Hello everybody and welcome back to Calculus 1. In our last lecture we talked about composite functions and we had an opportunity to do some exercises creating composite functions. So we should have a good feel for composite functions. So now we're going to talk about the next topic, which is the chain rule. Well, what's that? The chain rule tells us how to compute the derivative of a composite function. And here's what the derivative of a composite function looks like. Over here we have the composite function. We have f evaluated at g of x. And this is what the derivative of that composite function looks like. It's f prime evaluated at g of x times g prime of x. That's what the derivative of a composite function looks like. And I think I'm going to put this in a little box or a big box. This is the chain rule. And what I'm going to do next is I'm going to diagram the chain rule, just like we diagrammed the product rule and just like we diagrammed the quotient rule, that we're going to diagram the chain rule. This is a biggie. If we don't get this, we're going to be hurting in Cal 1. And if we take Cal 2 and we don't know this, we won't stand much of a chance. A lot of our success in Calculus 2 depends on how well we get down the chain rule and the analog of the chain rule that we'll see at the end of the course, which is called U substitution. If we get those two things, the chain rule and U substitution, if we get those two things down in Cal 1, Cal 2 is going to be a heck of a lot easier. So, without any further jibber-jabbering, let's get on to diagramming the chain rule. Here we go. Here's our chain rule, and we're computing the derivative of f evaluated at g of x. So we'll call f the outer function and g of x the inner function, since we're plugging g of x into f of x. So f is the outer, g is the inner. And here's what we get. We have f prime evaluated at g of x. So this is the derivative of the outer, f prime, evaluated at g of x, which is the inner function. So derivative of the outer, evaluated at the inner, times derivative of the inner. And I've written that in words. Here's the chain rule. The derivative of the outer, evaluated at the inner, times the derivative of the inner. Now, we want to say that several times a day for the next 3 or 4 days, just like we've been doing with the product rule and the quotient rule. Derivative of the outer, evaluated at the inner, times the derivative of the inner. The derivative of the outer, evaluated at the inner, times the derivative of the inner. Say it with me. The derivative of the outer, evaluated at the inner, times the derivative of the inner. Again, the derivative of the outer, evaluated at the inner. Tell you what, let me say it without me standing in front of it so you can actually read it, okay? Here we go. The derivative of the outer evaluated at the inner times the derivative of the inner. The derivative of the outer evaluated at the inner times the derivative of the inner. One more time. The derivative of the outer evaluated at the inner times the derivative of the inner. Now, if we say that several times a day for the next 3 or 4 days, we'll know it for life. And if we know that expression, then we can map out the chain rule and make a template for ourselves, just like we've been doing with the quotient and product rules. Okay, I think it's about time we did an example. Our first example: compute the derivative of sine evaluated at x to the 5th plus 4x cubed. Now let's identify the main characters here. The sine is our outer function, and x to the 5th plus 4x cubed is our inner function. And we know, according to the chain rule, what we're supposed to get. I think, let's see. The derivative of the outer evaluated at the inner times the derivative of the inner. Yeah, we know it. So let's write it out. We have the derivative of the outer evaluated at the inner times the derivative of the inner. So that looks good. Now let me do some scratch work over here. The outer function is sine evaluated at this mess. Now I'm going to write myself a note. I'm going to remind myself what the derivative of sine of x is. See, what is it? We should know that by now. The derivative of sine of x, what is it? Have we got it? Cosine of x? Okay. Now, our outer function is sine evaluated at something. That's the outer function, sine evaluated at something. So the derivative of the outer function let me think about this now. The outer function is sine evaluated at something. And I want the derivative of the outer function. How should I reason on that? Well, let's go back to what we know. the derivative of the sine evaluated at x is the cosine evaluated at x, or the derivative of sine of x is cosine of x. So what's the derivative of sine evaluated at something? Wouldn't it be cosine evaluated at something? If that's what you're thinking, you're right. The derivative of sine evaluated at x is cosine of x. The derivative of sine of something, or sine of something, is cosine of something. The derivative of sine evaluated at something is cosine evaluated at something. This is important because now we know what the derivative of the outer function is. So let's just write it down. Cosine evaluated at something. This is the derivative of the outer function. Are we done here? Well, our template says we need the derivative of the outer, which we have, but it has to be evaluated at the inner. In other words, we have to take the inner function and plug it in here. So we'll take the inner function, x to the fifth plus 4x cubed, and plug it into the derivative of the outer. Ah, that's great. And then we multiply by the derivative of the inner function. 5x to the fourth plus 4x cubed. And in case you're wondering whether we can really simplify this at all, the answer is no. We might have a tendency to want to multiply this polynomial by that polynomial, but that's not what's going on here. See, we have a product, but what is it that we're multiplying? We're multiplying the derivative of the outer, cosine of something, times the derivative of the inner. So this polynomial is not being multiplied by x to the fifth plus 4x cubed. This polynomial is being multiplied by cosine evaluated at x to the fifth plus 4x cubed. So really what this is 5x to the fourth plus 4x cubed times cosine of this thing. So we can't simplify this any further. And we can't take these two things and multiply them together. We're good just like we are right now. But we can always use more practice. So let's do a little bit more practicing. New example. And before we actually get into this, I just want us all to recognize what this thing is not. This is not cosine times sine of x. It's not cosine times sine of x, and it's not cosine of x times sine of x. This is not multiplication at all. And we might be wondering, well, how do we know? How do we know that this is not multiplication? And we can reason on it this way. If cosine evaluated at sine of x is multiplication, then we have to have two factors. And then we're going to have to identify what these factors are. So we have to have two factors. What are they? Well, sine of x could be a factor. And that doesn't bother me too much, but if sine of x is one factor, then cosine, just plain cosine and nothing else, yeah, there we go. Cosine is the other factor. Now, one of these things makes absolutely no sense at all. This is okay. This is meaningless. Just plain cosine. In order for this to make sense, we have to evaluate the cosine function at an angle. We have to have the cosine function evaluated at something. And I'll put this in quotes. Just plain cosine with no angle after it is absolutely meaningless. We have to have cosine evaluated at an angle. Okay, well, in this expression, what's the angle that cosine is evaluated at? The angle is whatever appears in this set of parentheses here. Cosine has to be evaluated at an angle. So guess what? This is the angle at which cosine, I wrote that awfully small, I'm sorry, at which cosine is evaluated. So this has to be a composite function. It has to be cosine evaluated at sine of x. Otherwise, we have cosine, and we're not evaluating cosine at any angle. And just plain cosine makes no sense at all. It's meaningless. Now, before we go on to do this exercise, I guess I do have to answer one more question, just to make sure that we understand everything. So we do need to answer this question. If this thing is not cosine times sine, or cosine of x times sine of x, then what does cosine of x times sine of x look like? And here's what it looks like. Cosine of x times sine of x. And notice the cosine function has its own angle at which it's evaluated, just like the sine function has its own angle at which it's evaluated. So each of these things individually makes sense. Cosine of x for lack of a better way of saying this, I'll say perfectly reasonable. And sine evaluated at x, perfectly reasonable. Each one of these things by themselves makes sense mathematically. So cosine of x times sine of x, if it's multiplication, this is what it looks like. Cosine with its own angle times sine with its own angle. Okay, we got all of that taken care of. And yeah, we killed a little time clarifying that, but I'll tell you what, maybe it was time well spent, because a lot of people will look at this expression and they'll say, cosine times sine, this is a product. Cosine of x times sine of x, like we have here, cosine of x times sine of x, that's a product. But cosine, sine of x, the only way that this can make sense mathematically is if sine of x is the function that we're plugging into the cosine function. The only way it makes sense mathematically is if this is function composition, and cosine is the outer function, and sine of x is the inner function. So we will proceed now with that understanding. So this is the outer function. And let me write that a little bit bigger. This is the inner function. It's a chain rule exercise. We know exactly what we're supposed to get if we've remembered that saying. Let's see, what is it? The derivative of the outer evaluated at the inner times the derivative of the inner. So let's write down what we're supposed to get. Derivative of the outer evaluated at the inner times the derivative of the inner. Now I'm going to do something that I did with the previous exercise. I'm going to plan everything out. I'm going to do some scratch work. Cosine's my outer function. So I'm going to remind myself what it is I know about the derivative of cosine. What's the derivative of cosine of x? Do we remember? That's the one that has the negative sign in front of it, isn't it? So derivative of cosine of x is negative sine x and I identify our outer function. It's cosine evaluated at whatever. So the outer function is cosine evaluated at something, or cosine of something. And we need the derivative of the outer. Now let's reason on this. The derivative of cosine evaluated at x is negative sine evaluated at x. So what's the derivative of cosine evaluated at something? Wouldn't it be negative sine evaluated at something? That's exactly what it is. Negative sine evaluated at something. The derivative of cosine of x is negative sine of x. The derivative of cosine of something is negative sine of something. So we'll write this down. Here's the derivative of our outer function. Negative sine evaluated at something. So derivative of the outer, that's it. Now what are we supposed to do? The chain rule says we're supposed to take the derivative of the outer, this thing, and evaluate it at the inner function. In other words, we take the inner function and we plug it in here. So we take sine of x and pop it right in. There we go. There's the derivative of the outer, evaluated at the inner, sine of x. And then we have times the derivative of the inner. Well, sine of x is the inner function, isn't it? So what's the derivative of sine of x? Cosine of x? Yep, you were right. Cosine of x. And there's our answer. Note that this is negative sine evaluated at sine of x. It's not multiplication. So we can't tidy this up by rewriting this as negative sine squared x, because this is not multiplication here, is it? This is as simplified as we can possibly get it. Well, let's see. Time for another exercise. This exercise looks harmless enough, but it has an interesting twist. It really does. It's a nice exercise. And let's diagram it. The outer function here is secant of something. the inner function is x to the fifth. So this is a composite function. This definitely is a composite function, which means we use the chain rules. Help me out here. What does the chain rule say? The derivative of the outer evaluated at the inner times the derivative of the inner. So we have the derivative of the outer evaluated at the inner and then times the derivative of the inner That's what the chain rule says that we get. And as I did before, I'm going to plan this out. I'm going to write down my scratch work. And my outer function is secant evaluated at something. And I'm going to have to compute the derivative of the outer function. So to start off, I'll write down what I know about derivatives of secants. What I know is that the derivative of secant evaluated at x, you know what, I think I need to write that larger. What I know is that the derivative of secant evaluated at x, at least I think I know, help me out. What's the derivative of secant of x? Do you remember? It's one of those 6 trig derivatives that we have to remember. And we do want to memorize these things. Pattern recognition is often a big part in a student's success of mathematics, and an even bigger part of a mathematician's success in mathematics. We never get to the point where we're so good at math that we can throw pattern recognition out the window. As a matter of fact, the better we get at math and the deeper we get into math, the more we rely on pattern recognition. So, do we know the derivative of secant of x? See, it's secant of x times tangent of x, isn't it? So let's write that down. Now, our outer function is secant evaluated at something. That's the outer function. And we want the derivative of the outer function. Well, let's reason on this now. The derivative of secant evaluated at x is secant evaluated at x times tangent evaluated at x. Or let's say it this way. The derivative of secant of x is secant of x times tangent of x. So the derivative of secant of something is going to be secant of something times tangent of something. That's exactly what it is. It's going to be secant of something times tangent of something. That's the derivative of the outer function. Excellent. And maybe I should have allowed myself a little bit more room over here. So first thing we do, we write down the derivative of the outer. Secant of something times tangent of something. Okay, there's the derivative of the outer. And what do we do next? The chain rule says we evaluate it at the inner function. So we take the inner function and plug it in. But wait a minute. Just exactly where are we going to plug this inner function? Here? Here? Well, when we compute the derivative of secant x, where do we plug in x? Here? Or here? We plug it in both places, don't we? And we're going to do exactly the same thing when we plug in x to the fifth, the inner function, to secant of something times tangent of something. The inner function x to the fifth goes both places. And that was the little trick, the interesting feature of this exercise that I mentioned. The inner function is plugged in two different places. So here's the inner function. And here we plug in the inner function again. Ah, wonderful. And last but not least, we multiply by the derivative of the inner function, 5x to the fourth. And we can leave it like that. Some people, if they have a product of polynomials and trig functions, they like to put the polynomials out front. So I'll put the polynomial, 5x to the fourth, out front. And then I have secant x to the fifth tangent x to the fifth. And we pat ourselves on the back and say, bravo. Well done. Okay. Another derivative exercise. How do we do this one? What do you think? Am I being sneaky here? Absolutely. Because you look at this and you think, wait a minute, we've been down this road before, sort of. We look at this and say, I don't see that this is a composite function. I don't see that this is one function evaluated at another. And when we say that to ourselves, we're right. This is not a composite function. What is it? This actually is sine of x times cosine of x. This actually is a product. So we're not going to use the chain rule. We don't use a chainsaw to hammer nails. We use the chain rule to compute the derivatives of composite functions. But when we compute the derivatives of products, we use the product rule. So let's see, we're going to have the first, the second, and then we need to remember what the product rule says. First prime times second plus second prime times first. Oh, okay. So we're going to have first prime times second plus second prime times first. That's the product rule. We have diagrammed this according to the product rule. First prime times second plus second prime times first. So we fill in the blanks. First prime, that's the derivative of sine of x. What is that? Cosine of x? You're right. Times the second verbatim, so that's cosine of x, plus the second prime, derivative of cosine of x. Yep, that's the one that has the minus sign in front of it. So minus sine of x times the first verbatim, which is sine of x. And I'd probably simplify this a little bit. Now this really is multiplication. First prime times second, second prime times first. So it's cosine of x times cosine of x, cosine squared x, minus sine of x times sine of x, sine squared of x. More exercises. What happens if we have the composition of three functions? F evaluated at g, evaluated at h of x. How do we do that? You know, this is rather reminiscent of when we were working with the product rule. And we were trying to figure out how do we compute the derivative of the product of three functions. And the problem seemed to be that the product rule that we knew only told us what to do if we have the derivative of the product of two functions. And so the way we had to attack that, we had to look at the product of three functions and analyze it as being the derivative of the product of two functions so we could apply the product rule. We have a similar dilemma here. The chain rule only tells us how to compute the derivative of the composition of two functions. We have the composition of three functions here. So it looks like we're going to have to view this in a special way. Now remember what the chain rule says. The derivative of the outer, evaluated at the inner, times the derivative of the inner. So when we're applying the chain rule, we look at the function that we're computing the derivative of as being an outer function evaluated at an inner function. So any chance of success computing the derivative of the product of three functions hinges upon us analyzing this as an outer function evaluated at an inner function. So at least for now, that's how we have to approach it. And I'm thinking, okay, call f the outer function, and everything else we'll call the inner function. And we know what the chain rule says. The derivative of the outer, evaluated at the inner, times the derivative of the inner. So let's write that out. Derivative of the outer evaluated at the inner times the derivative of the inner. So the derivative of the outer, well, the outer function is f evaluated at something. So the derivative of the outer function is f prime evaluated at something. So there we go. This is the derivative of the outer. And what we have to do next is we have to evaluate it at the inner function. Or we have to take the inner function and plug it in here. Well, the inner function is g evaluated at h of x. So we plug that in. Beautiful. We got the derivative of the outer evaluated at the inner. Now we have to compute the derivative of the inner function. Ooh, the inner function's a composite function. We have to use the chain rule to compute the derivative of this thing. But we're already right in the middle of the chain rule. So what I'm going to do is I'm going to delay applying the chain rule to this composite function because I'm already in the middle of the chain rule. But I'm going to write myself a sticky note to make sure I do that in the next step. There. Now, technically, this is the derivative of the inner function. We just haven't computed explicitly what it is yet. And I'm going to wait until the next step before I do that. I just hate to use two rules at once. I get all confused and I forget where I am in the process, so I try to do one thing at a time if I can. So I have f prime evaluated at g of h of x. Times the derivative of this thing. Well, this is just the composition of two functions. We know how to do that. The derivative of the outer, which is g prime, evaluated at the inner, h of x, and then times the derivative of the inner. Okay. This is what it turns out to be. And I'm going to erase the board and write the result down again, just so that we can analyze it. Here's our result, written again. And we're told, note the pattern. And there is a pattern. Notice what we start off with. The derivative of the outermost function. So f of x is the outermost function. So we compute the derivative of the outermost function, evaluate it at everything inside, and then what do? We move in to the next outermost function, and we have the derivative of the next outermost function, evaluated at everything inside of it, and then where do we go? We move in again to the innermost function, h of x, and compute the derivative of the innermost function. So when we compute the derivative of composite functions, we always start at the outermost function, and we have derivative of the outermost function, evaluated at everything inside, And then we move into the next outermost function. Compute the derivative of the next outermost function, evaluate it at everything inside of it, and then we move in again, derivative of the inner function. This is how we compute the derivative of the composition of three functions. Now, if we see this pattern, then it shouldn't be much of a big deal to extend the pattern to the composition of four functions. And you know when we did the derivative of the product of three functions, and I said, well, you'll see this some, but not much. And then we did the derivative of the product of four functions, and I said, outside of this Calculus 1 class, we may never see it. It's not going to happen very often. Well, the analogy is not quite true with the derivative of composite functions. The derivative of the composition of three functions, that's not going to be unusual at all. Not at all. And the derivative of the composition of four functions, it'll be somewhat unusual, but we'll see it. And we'll see it periodically. So we need to know how to extend this pattern to the composition of four functions. So let's see if we can do it. I'm going to make a little room for myself here. Whoops. And I'll write outermost. So we have derivative of f evaluated at g, evaluated at h, evaluated at k of x. And the first thing we do is we start with the outermost function. So here's the outermost function. And we compute the derivative of the outermost function evaluated at everything inside. So derivative of the outermost function evaluated at everything inside. So that would be g evaluated at h, evaluated at k of x. Then what do? We move in to the next outermost function, g, and we compute the derivative of the next outermost function, evaluated at everything inside of it. So we'll have g prime. Yipes, I got carried away there. G prime, evaluated at everything inside of it, h, evaluated at k of x. And then what? We move in again to the next outermost function, h. We compute the derivative of the next outermost function, that's h prime, evaluated at everything inside of it, k of x. And we keep on moving till we get to the inner function. When we get to the inner function, we compute the derivative of it, k prime of x. And again, I'll say note the pattern. The composition of more than two functions, we'll see it. We'll see it all the time. Here we go. The derivative of the composition of three functions. Now, do you remember where we start? If you said the outermost function, then you were paying attention. the outermost function So the strategy is to compute the derivative of the outermost function, evaluate it at everything inside. And what's the derivative of cotangent of something? See, what's the derivative of cotangent of x? See, negative cosecant squared of x. So the derivative of cotangent of something is negative cosecant squared of something. So negative cosecant squared evaluated at the inner function, secant x to the fifth, okay. We have the derivative of the outermost function evaluated at everything inside. So now we move in one layer to the next outermost function. And we have the derivative of secant of something evaluated at everything inside of it. What's the derivative of secant of something? We'll make it easy. What's the derivative of secant of x? Secant of x times tangent of x. So the derivative of secant evaluated at something is secant of something times tangent of something. So here's the derivative of secant of something. So this is the derivative of secant, and it has to be evaluated at everything inside of secant. So where does this x to the fifth go? Do you remember? It goes in both places, doesn't it? So we have x to the fifth here, x to the fifth here. Excellent. Oh, but we're not done. Then we have to keep going till we get to the inner function. And we multiply by the derivative of the inner function. 5x to the fourth. Okay, I think I'll stop here. That was a long one. Here's a brain teaser. We've got a composite function, sine evaluated at this thing. We've also got a quotient. Now it seems like we should use the chain rule because we have a composite function. But it also seems like we should use the quotient rule because we have a quotient. Which one do we use? Which one do we use? Do we use the chain rule or do we use the quotient rule? And why? Here's the way to approach something like this. Look at the expression that we're computing the derivative of and ask ourselves, in the most general sense, what is this thing algebraically? In the most general sense, is this one function evaluated at another? Or in the most general sense, is it the quotient of two things? Can we look at this entire expression as being one thing divided by another? And you know what? I don't think we can analyze this whole expression as being the quotient of one thing divided by another. But we can analyze this whole thing as being the sine function evaluated at this quotient. So in the most general sense, this is a composite function. And this is a key observation. In the most general sense, this is a composite function, so we're going to use the chain rule. And maybe some of us are saying, but what are we going to do about this? It's a quotient. Don't worry about it. Just worry about the fact that in the most general sense, this is a composite function. So we're going to use the chain rule. So this is the outer function, and this is the inner function. And I guess I'll do my scratch work again. And we recall the derivative of the sine of x. So our outer function is the sine evaluated at something. And the derivative of the outer function well, let's reason on this now. The derivative of sine of x is cosine of x. So what's the derivative of the sine of something? Cosine of something? The derivative of the sine of something is cosine of something, or cosine evaluated at something. So there's the derivative of the outer function. And now I'll plan this thing using the chain rule. Derivative of the outer evaluated at the inner times derivative of the inner. So derivative of the outer, whoops, I got more than the derivative of the outer, don't I? Derivative of the outer times derivative, no, that's not right, derivative of the outer evaluated at derivative of the inner times derivative of the inner. So that's what I'm supposed to get. And I know the derivative of the outer function. It's cosine evaluated at something. So here's derivative of the outer, cosine evaluated at something. And we evaluate this, whoops. Why did you people let me go on? Derivative of the outer evaluated at the inner okay, derivative of the outer, cosine evaluated at something, times evaluated at the inner, this quotient, so 3x squared plus 2 all over 5x cubed, derivative of the outer evaluated at the inner, times derivative of the inner, oh no, the inner function is a quotient. I have to use the quotient rule to compute the derivative of this thing. But I'm right in the middle of the chain rule. I don't want to start another rule right now. And I hate to use more than one rule at a time. So I'm going to postpone using the quotient rule. What I'm going to do, I'm going to write myself another one of these sticky notes. The derivative of 3x squared plus 2 over 5x cubed. There. Now technically this is the derivative of that expression. We just haven't computed it explicitly. But I'm going to wait until the next step before I actually compute this thing explicitly, because I hate to use more than one rule at a time. Well, I just finished using the chain rule. So now on the next step, I can compute this thing. So I have cosine of 3x squared plus 2 over 5x cubed times the derivative of this piece of junk, and it's a quotient. So let's see, top prime times the bottom minus bottom prime times the top, all over the bottom squared. So top prime, that's going to be 6x, times the bottom, 5x cubed, minus the bottom prime, 15x squared, times the top, 3x squared plus 2. So let's see, do I have it? Top prime times the bottom, minus bottom prime times the top, all over the bottom squared, and we did that by the quotient rule. And I don't care, I'm not going to simplify this for anybody. Unless maybe this is a homework exercise from the text, in which case I'll simplify it as much as I can or as much as I have to make sure that this is equivalent to the answer that they have in the back of the book. But I'm not going to simplify this any more than I have to. I am just not that much of a glutton for punishment. Now, before we go on to one last exercise, let's do a retrospective of this, okay? A retrospective of what we just did. When two rules of differentiation, that is, two rules of computing derivatives, seem to come into play simultaneously, like the quotient rule or the chain rule, and we say, well, I don't know which one to do. We have a quotient, we have a composite function. Do we use the quotient rule? Do we use the chain rule? When two rules come into play simultaneously, or they appear to come into play simultaneously, we ask ourselves this question. In the most general sense, how do we classify or analyze the expression? Is it a composite function? Is it a quotient? Is it a sum or difference? Is it a product? Our answer to this question will tell us which rule to use first. If we analyze the expression as being a composite function, we use the chain rule and don't worry about the other rules. If the answer to this question is our expression is a product, then we use the product rule and we don't worry about anything else. If the answer to this question is a quotient, then we use the quotient rule first and don't worry about the other rules until we're forced to. So this is the rule of thumb that we use when two rules of differentiation seem to come into play at the same time. Look at the expression and say, in the most general sense, how do we classify this thing algebraically? The answer to that question will tell us what rule to use. This is a nice one. Given that capital T prime of x equals 1 over 1 plus x squared, or d dx of t of x is equal to 1 over 1 plus x squared, compute the derivative of t evaluated at tangent x. Now, one thing that makes this kind of an unusual exercise is that we're not told how the function capital T is defined. We're told what the derivative of capital T is, but we're not told what capital T of x is. Doesn't matter. The fact of the matter is that we're computing the derivative of a composite function, and capital T is the outer function, and tangent of x is the inner function. So this is what we're looking at. The derivative of t evaluated at tangent of x here's the outer, here's the inner. So we know what we're supposed to get. Derivative of the outer evaluated at the inner times derivative of the inner. That's what we get. And maybe I'll do a little scratch work over here, because this is somewhat of an abstract exercise. We'll write down what I do know about capital T. The derivative of capital T of x is 1 over 1 plus x squared. And capital T is the outer function. So the outer function is t evaluated at something. And what about the derivative of the outer function? Well, the derivative of t of x is 1 over 1 plus x squared. So what about the derivative of the t? What about the derivative of t of something? Wouldn't that be 1 over 1 plus something squared? This is the derivative of the outer. And if we see this much, we probably can do the whole exercise. The chain rule says we should have the derivative of the outer. That's this thing. So 1 over 1 plus something squared That's the derivative of the outer. And now we have to evaluate it at the inner. Tangent of x and let's see, the derivative of the inner function. What's the derivative of tangent of x? Secant squared of x. So let's see, secant squared of x. And that is our derivative. In our homework exercises, we will have a couple like this. So this one might be well worth studying, as will most of the others. And are we done with the chain rule? Not by a long shot. The chain rule is very important, so we're going to spend a few lectures on this just to make sure we get it right.